Okay. Thank you, Jonathan Lindell from Uppsala University for accepting our invitation. Be welcome here uh, on your talk on the first relative Hochschild cohomology. Thank you. Start whenever you want.
Yes, thank you very much for the invitation and for letting me speak the seminar. So yeah, as said, I will talk on the first relative Hochschild cohomology. Um, I will start by saying that this is all joint work with Lleonard Rubio y Degrassi. So, to start off with, throughout the talk, we're going to let A denote the K algebra, where K is going to be a field, usually algebraically closed. Then the enveloping algebra of A is defined to be A tensor over K with the opposite algebra. And then the reason why we look at the enveloping algebra is because left module stands over the enveloping algebra, then of course equivalent to bimodules over algebra that we start with. And then using this, we can define the Hochschild cohomology of an algebra to be in degree n the n extensions of the algebra as a bimodule. Equivalently, this can also be computed as the cohomology of the complex we get by applying the Hom functor to the Barra solution of A. So specifically, we have a differential given as follows. So if f now is a map taking in n number of inputs, putting one input, then we can apply this in a higher degree by either multiplying on the outside to the left or the right, or we can multiply on the inside first and then apply f and take the alternating sums of these. Okay, so now we have the definition of Hochschild cohomology, but what does this actually tell us about the algebra? Well, then using the Barra solution that we had before, one can compute that in degree 0, the Hochschild cohomology of the algebra is just isomorphic to the center of the algebra. In degree 1, we get that this is isomorphic to derivations of our algebra quotient by inner derivations. So what do we mean by a derivation? Well, a derivation is then a linear map from A to A, such that this fulfills the Leibniz rule. I.e., if we apply now our map to a product, then we can decompose this as applying it to the first element in the product plus applying it to the second. And by inner derivation, we mean a derivation that's given by the commutator with respect to some element. And then lastly, degree 2, one can show that degree 2 of the Hochschild cohomology controls the infinitesimal deformations of the algebra. So, for example, if one is interested in understanding the deformation theory of an algebra, we of course nice to understand the Hochschild cohomology. And now we can note that in degree 1, we have the structure of a Lie algebra where we take the commutator of our derivations. So composition of derivations will not generally be a derivation, but the commutator will actually give us derivation. So this gives us the structure of a Lie algebra. And in general, it was shown by Gerstenhaber that you have a more general structure called the Gerstenhaber algebra in Hochschild cohomology, extending this Lie bracket. And then it was shown by Keller that this is a derived invariant together with this Gerstenhaber algebra structure. So in particular, if we're interested in HH1 and its Lie algebra structure, this is a derived invariant as a Lie algebra. One problem with Hochschild cohomology, even though it's parentheses very nice things, is that in general, of course, Hochschild cohomology is very hard to compute. For example, we always have the Barra solution, of course, but this grows very large very quickly. So one thing one can do then is to start by trying to understand degree 1 of the Hochschild cohomology and its Lie algebra structure and see how that behaves to get an idea then. And this has been studied in earlier work by Stramets and Sanchez-Flores, for example, studying the Lie algebra structure of monomial and radical square zero algebras. And also Chaparro, Schroll, and Solotar studied also the solvability of the first Hochschild cohomology for gentle algebras and Brouwer graph algebras. And then it was shown by Rubio y Degrassi, Schroll and Solotar, also by at the same time by Rubio y Degrassi and Linkemann, and implicitly in the work of Eichler and Rudgelders, that we have the following sufficient condition for solvability of HH1 of an algebra. So the setup is as follows. So we let K now be an algebraically closed field, and then A is some finite dimensional algebra. And then if the Gabriel quiver of A has no loops nor parallel arrows, then one gets that HH1 of A is a solvable Lie algebra. So from the shape of the quiver, we can then see that we have solvability of HH1 of A. And also, to give a context of interest in HH1, in the context of group theory, if we now let G be a finite group, gain a heuristic prime heuristic P, and then let B be some non-semisimple block of the group algebra, then it's an open conjecture by Linkelmann that the HH1 of the block is non-zero. This is, for example, known in the case of the symmetric groups, blocks of symmetric groups. But in general, it's an open question. So even the non-vanishing of the Hochschild cohomology in degree 1. And so now we're in the setup where we would like to study HH1 and see how it behaves and so on and so forth. And it would be very nice if we were able to use the flexibility of, I don't know, taking morphism and saying, oh, HH1 and the target object behaves like this, so we can say something about the object that we had before, or we can take subalgebras, etc., to study our Hochschild cohomology. But problem, of course, is then, as we saw earlier, degree 0 of the Hochschild cohomology is the center. So Hochschild cohomology is not functorial on the category of algebras. So in general, for example, take some subalgebra of interest. Let's say we have some subalgebra. In general, we won't get a map from the Hochschild cohomology of the subalgebra to the Hochschild cohomology of the big algebra. So what can we do then? So one solution, or one idea, is then we can look at what's called instead the relative Hochschild cohomology of this pair. So we can then study the Hochschild cohomology relative to our sub-object. Okay, so that now begs the question, what is then relative Hochschild cohomology and what is more generally relative homological algebra? So relative homological algebra was defined first in the 50s by Hochschild, and then he also defined relative Hochschild cohomology. So the setup is as follows. We let B to A be a morphism of K algebras. And then we say that a complex of A modules, so we're going to always work here in the category of A modules, so we're working in the category of modules over big algebra, is relative exact if, okay, first of all, it's exact, but then we have a second assumption that the complex splits as a complex of B modules. So when we take the forgetful functor to the category of B modules, then this complex should split. So let's give an example then, just to see what this means in practice of such a complex. So now if M is any A module, then we can of course apply the forgetful functor and then induce. I can take the tensor product of M with A over B. And then we have a math epsilon here, which is given by the action. And then we can take the kernel. So this is short exact sequence. So this is obviously exact. But we can also see that we have a splitting of the short exact sequence by sending M to one tensor M. And this is only split over B, not over A, but this works since the tensor product is taken over B, so we can move out the left action. And this actually works. Okay, so now we have this idea of what it means to be relative exact. So using this, one can define what it means to be relative predictive. So we say that a module P is relative predictive if for all f from P to n and all f is g m to n that split over B, there should exist an h completing this triangle. So the difference here compared to a normal predictive module is that we assume that our surjection that we have there is not only just a surjection, but also splits over B. And then there's the lemma given by Hochschild in this written article that P is now relative predictive if and only if P is a summon of an induced module. So in general, for this setup of relative homologic algebra, we get more predictive modules if all the induced modules are predictive, but we have less exact sequences since we have stronger assumptions there. And then now that we have predictive modules and we have a functional exactness, we can define a relative predictive resolution akin to normal case to just be a resolution where the modules appearing instead of being predictive are then relative predictive, and the whole, if we add the epsilon map there from P0 to M, this whole complex that we get will then be relative exact instead of just being exact. And I should note that every module has a relative predictive resolution by just repeating this example here. Since by the lemma, A tensor M over B is predictive, then we just can continue on like this and build a predictive solution. So this, then, since we are also in the setup where we have enough predictives, we can now define the relative x functor of two modules to be the cohomology of the complex we get by applying the Hom functor, the contravariant Hom functor to a relative predictive resolution instead of a normal predictive resolution like we do in the standard setup. Whoops. So yes, and then we can note that okay, if we now have an homomorphism B to A, then this in turn induces a morphism of the enveloping algebras. So in particular, we can define then the relative Hochschild cohomology to be the relative x with respect to developing algebras of A. And one can show that this is the same as the cohomology of the complex that we get where we apply contravariant Hom functor to the relative Barrow solution. So as you see there, instead of having Homs now over k of A tensor over k n times in J, we instead tensor over B. Then we get, and this is these are projectives, well, before we apply n+2 by the lemma again that we had earlier. So, okay, so now we have this definition like we had before, but okay, what does it actually tell us in the low degrees? So using the complex then, the relative Barrow solution, one can show that degree 0 of the relative Hochschild cohomology will yet again be the center. So the 0 degree does not depend on B. And secondly, one gets that degree 1 of the relative Hochschild cohomology is isomorphic to derivations of A with respect to B, quotient by inner derivations of A with respect to B. Okay. What do we mean then by a derivation of A with respect to B? Okay, so a derivation of A with respect to B is just a derivation that vanishes on the B part. And similarly, an inner derivation with respect to B relative to B is just an inner derivation that vanishes on the B part. And then similarly, the absolute case, HU2 controls something like the B relative infinitesimal deformations of A. And then we can note, yet again, that the relative in degree 1 also has a structure of a Lie algebra under the commutator. And then we have the following lemma, which is given in several places, that we get an inclusion of Lie algebras of the relative into the absolute for all morphisms of B of A. So when we take morphisms of subalgebrics, we then get Lie subalgebras. So for example, if we're interested in solvability, we see that if HH1 of A is solvable, then the relative will be solvable. So let's look then at an example of how the relative Hochschild cohomology behaves compared to the normal Hochschild cohomology. So assume now that K is field characteristic different from 2, and we let A be the path algebra of the quiver where we have Kronecker there in the top, and then beta going in the other direction. And then we quotient out by the ideal that's given by first going along beta, and then either alpha 1 or alpha 2 is 0. So we let A be this algebra, and we take B now to just be the Kronecker part. And this is the subalgebra of A. And then one can compute that the absolute Hochschild cohomology is isomorphic to SL2 of SL2 of with respect to field times K, and that the relative Hochschild cohomology in this case is just isomorphic to K. But then we can note that HH1 of A is not solvable since we have the SL2 pairing there, whereas the relative is definitely solvable since it's just K. So it can definitely happen then that we have solvability of the relative, but not solvability of the absolute. So this was the first thing we looked at then, is can we understand when we get solvability then of the relative. So now we're in the following setup then for this condition. So we let A be some path algebra, a quiver quotient by some admissible ideal. And then we let B be a subalgebra generated by taking a subset of arrows. So for example, in this case, the subset arrows to pick are alpha 1 and alpha 2. And then we denote by QC the quiver where we remove all the arrows in B from the arrows in A. So we don't remove the idempotent, but like we take away the arrows that we have in in B from A. And then we get the following result. So if now again we take K now to be an algebraically closed field, A and B are given as above, and we assume that A is finite dimensional. Then if the complement of our QC here has no parallel arrows or no loops, then we get that the Hochschild cohomology of A relative to B is solvable Lie algebra. And then we can note that if we take B to be generated by the empty set of arrows, then B is just given by the semisimple part, and in particular, in this case, the relative Hochschild cohomology is just isomorphic to the absolute Hochschild cohomology. And then this also, Q of C is just the whole quiver, so this generalizes the earlier result. So what is the idea? How do we show this? Just given try your sketch of the proof. So we have by earlier theory the following map there from HH1 of A to HH1 of A quotient by the radical squared. And then in particular, we show that if we first take the inclusion and then this map, we get an induced map into the relative part where we yet again take radical quotient by the radical squared. And then we can get control over the kernel of the top map, which more typically that it's an nilpotent ideal. In particular, we get that the kernel of the bottom dash map is an nilpotent ideal. In particular, it's solvable. And then the nice thing about the right-hand side is that since we're quoting out by the radical squared, this is all monomial. So then we can really compute stuff there using Stramets and the theory developed by Stramets and Sánchez Flores, and show that the derived subalgebra on the right-hand side is abelian, thus implying that the image of the derived subalgebra of the image is abelian. But then we have that image, in particular, solvable, the kernel is solvable, so then we get that the relative is solvable. So, and this is then how we show this. So looking back now at the example we had before, we can see directly that, okay, Q of C here in this case, since we're removing B, is given by alpha 1 and alpha 2. And since we're now removing the arrows alpha 1 and alpha 2, we're just getting beta that's left. So there's no parallel arrows, no loops. So then directly we see that the relative will be solvable in this case. Just as a remark, note if we let C now be the subalgebra then generated by the arrows in QC, then note that the relative Hochschild cohomology in this case is not the same as just taking the Hochschild cohomology of the complement. And in general, it's unfortunately not often the case that it would be very nice if it was, but Hochschild cohomology of the absolute Hochschild cohomology does not generally decompose as the relative and as the B part. But motivated by finding examples where this actually happened, we next studied dual extension algebras. So what is the dual extension algebra? These were first done by Shang Shi. So we take two quiver algebras such that their set of idempotents agree. Then the dual extension of B to A of is given by taking the quiver where we have the same idempotent, just fixing idempotents. And the arrows are given by union of the arrows of the two algebras, except that we flip one of them. In this case, the A part. And then we take the relations to be the relations that we have in the A part and the B part, plus the additional generators where we say that going from the A part up to the B part, so to speak, arrows should be 0. Okay, so this is much clearer if we just do a simple example. So now, if we just let A and B for ease now be the same quiver, so we have that A and B are both just the A2 quiver. Then what we do is we take another copy of the A2 quiver, we flip it around, and then we glue on. Then we get the quiver given by these two arrows. And then we are supposed to also introduce this generator, which says that first going alpha and then going beta is 0. So this is the dual extension algebra of A2 then by itself. And these appear, for example, this specific algebra appears in, for example, in the representation field SL2. Okay, so before we can state the result, just need to recap some things about monomial algebras. So if we have now that A is a monomial algebra, and then we can denote Z generators of our ideal, and the squiggly B by the basis of path. And then we define this vector space K, small k of K parallel to squiggly B, and to be the vector space generated by all paths K and P such that they are parallel. And then it was shown by Stramets that the Hochschild cohomology of a finite dimensional monomial algebra can be computed via the following complex. So the first part is everything, all the paths in B that are parallel to idempotents, then to arrows, and then to generators or relations. In particular, we have a grading there on the term in degree 1, given by just the length of the right hand side. So in particular, for the monomial case, we get an induced grading on HH1 of A from the grading that we have in in the complex. And then we managed to show that if we take A and B to be directed monomial algebras, such that the vertices are the same and they have the same ordering. So we only, I mean by directed is that we have some ordering on the vertices, and then we only have arrows going in increasing direction of this order. Then we have that in degree 1 of the degree 1 of the Hochschild cohomology decomposes as the dual extension of the dual extension decomposes as the relative part, which would be, and the B part as three elements. And then in particular, if we make additional assumptions now on A and B, so we assume that they are radical squares of 0 and they don't have any loops, then degree 1 of the Hochschild cohomology in degree 1 is the whole thing. This is the only thing that we have. So then we get an actual decomposition of the Hochschild cohomology of the dual extension one as the Hochschild cohomology in degree 1 of the B part and the relative. So for example, in this case, we can then say that if the B part is the B part and the relative part are solvable, then the absolute part are solvable. In general, unfortunately, it seems to be a bit tricky to understand when we get solvability on the big part from just solving the relative and the subalgebra part. But yet again, we've seen here earlier that solvability really depends on the shape of the quiver. So by this reason, we were interested in trying to understand how the fundamental group behaves and the relative setup. Since there's this sphere of fundamental groups quivers which connects to the Hochschild cohomology. So let us first then recall what is the definition of a fundamental group of a quiver as given by Martinez Villa and de la Peña in the 80s by covering theory. So the setup is as follows. Yeah, so okay, so the point of this, as I see at least, is that this will tell us information then about the first Hochschild cohomology only from the topology, so to speak, of the quiver. So the setup is we take some A to be some algebra which connected Gabriel quiver. One can do it if it's not connected, it's just equation is easier. And then we fix a complete set of orthogonal idempotents, so E1 up to En. And then a presentation of an algebra, with this we mean a surjective algebra map from some path algebra from quiver to A, such that we get a bijection between the idempotents and vertices in our quiver. And to get more general representations, we do not assume in general that the kernel by I is admissible, nor that the idempotent needs to necessarily be primitive. And then we can say that elements then in I, the kernel here, call those relations, and we say that they are minimal if no proper subsum such relation is contained in I. We take the smallest sums in some sense. And if we now give an example then, so if we take, for example, G to be a group, then we can take the quiver with one vertex.
Is there an assumption that I is generated by elements that are in the ideal generated by the arrows?
Sorry?
I mean, you say that the ideal does not have to be admissible, but the ideal is generated in the ideal generated by the arrows.
Yes,
or can you have idempotents there in the ideal also?
No, good question. Sorry, I should remember this, of course.
Don't know. Probably in the square of the ideal generated by the arrows, you don't want.
Yeah, probably yes.
Okay.
Yeah, sorry, I should remember. Oh, thank you for the question. Okay, so if we have a group now, then we can take a presentation where we have just a quiver given by one vertex, then a loop for each element in G, and then we have a presentation given by just sending the loop to the respective element in the group algebra. And now that we have presentation, we can then define what we mean by walk. So a walk we define to be a zigzag of arrows in Q. So just walking around the quiver without keeping notes of which direction the arrow points. And then we have the following elementary homotopies on our walks. So first off, say that if we now walk in the opposite direction of some arrow and then walk the arrow back, then this should be the same as just the walk given by just staying at the terminal vertex of our arrow. And similarly, if we walk along some arrow and walk back, this should be the same as just staying at the starting vertex of our arrow. And then we have the second elementary homotopy, which says that now if P and Q are two paths which appear as elements with non-zero coefficients in some minimal relation, then we assume that we make these homotopic. And then we let I tilde I be the homotopy relation then generated by these elementary relations. And then we can define the walk QEI to be all the walks that start at EI and then at EI, i.e. all loops. And then we can apply pi1 of our algebra with the specific presentation here, so it depends, of course, heavily on the ideal, to be precisely these walks quotient by the homotopy ideal that we have, the homotopy relation that we have above, given by the ideal. So, for example, if we had the presentation we had before of the group, then in this case we precisely get that pi1 of the presentation of the fixed base point is precisely the isomorphic to G. So let's look now on an example then of a path algebra. And so if we take A now to be the path algebra, which is first, and then Kronecker between 1 and 2, then gamma from 2 and 3, and we have the relation that the top path, given by first taking going alpha and then going gamma, is 0. Then in this case, since in particular it's monomial, the second elementary homotopy won't come into play since we no such sums appear. So it's only the first one. But then since we have a hole here given by the Kronecker part, we get that this is just topologically a circle. So pi1 of our quiver with respect to the ideal is just isomorphic to Z. Okay. So what if we now take the same quiver, but we now instead take the relation where we have that the path gamma alpha is equal to gamma beta. Okay, but then by the elementary homotopy, this in particular means that gamma alpha is homotopic to gamma beta, but then particularly alpha is homotopic to beta by concatenating with gamma to remove the gamma, with gamma inverse to remove the gamma. So then this relation that we have here, in some sense, covers the hole that we have in the Kronecker, and therefore we get topologically that this is really just a disk, and the fundamental group in this case then is trivial. But the interesting thing here is that one can notice algebras, these two are isomorphic. So unfortunately, the fundamental group is not varying to isomorphism. So one solution then for fixing this is the following. So if we now take the space of all homomorphisms from the fundamental group into our field as an additive group, then we can define the pi1 rank of our algebra to be the maximal of the dimensions of the fundamental groups given by these different presentations. So depending on the presentation, as we saw, for example, in the earlier example, we get, in one case, the fundamental group was trivial, and in one case it was said. And then it was shown by Briggs and Rubio y Degrassi that the pi1 rank is a derived invariant. So the solution, or one solution we can see it, is then that we can look at all different presentations and all the fundamental groups that we can get in this case. Okay, but what is the connection with Hochschild cohomology? So to define this, we need one more definition. So a parade data, gamma, this we mean a choice of walks from our fixed base point to every vertex of the quiver. So it just tells us how to get to one from a base point to any other vertex in a fixed way. And then it was shown by Martinez-Villa and De La Peña, also De La Peña and Sorin, that there is an injective map from the dual of the fundamental group to the first partial cohomology given by the following formula. So what is this closure, or CL of gamma that I've written here? So let's look at the next slide just to explain how this map works. So P, we have some map from our fundamental group into our field. And then we take some element P in our algebra. Okay, then we can take a representative of that class, would be some path in our algebra. And then we can note that first we can take the parade data then from our fixed base point star here to the starting of P, starting vertex P. And similarly, we can take our parade data going from the terminal point of our path P to our base point star. But then we see here that we have precisely a loop. So this is an element of pi1 of the fundamental group. So then, in particular, we can then apply our function f to this to get a scalar, which we then can multiply our path p by. And this is the map that we have. So now we see that we then have that the shape, the fundamental group then maps into H1 and tells us information about H1. So if we recall from earlier, we're now in the following setup. So we have the dual of the fundamental group maps into the first Hochschild cohomology. And we also have the fact that the relative Hochschild cohomology maps into the absolute Hochschild cohomology. And then it would be nice to be able to fill in the question mark here and see what happens, what would be the equivalent thing to the fundamental group in this relative setup. And this is what we call the contracted fundamental group. So to define this, we now let N of B be the normal subgroup generated by elements of the following form. So star here is our fixed base point, and then V is some path in our A part, and then U and U prime, the dashed arrows here, are paths, or sorry, walks, not paths, walks in our B part. And then the contracted fundamental group we define then to be the fundamental group that we get by quotienting the fundamental group by this normal subgroup. So how we think about this is that this, if the B parts were contractible, then this, of course, this generators that we have above here would just contract, would just be trivial by the homotopy, since V and V minus 1 are the same path, the same walk. So what we're doing kind of like this is we're locally contracting all the B parts. So it's not like we're identifying everything in B to be the same, but just locally filling in or like contracting whatever it is there. So let's look at an example to make it a bit more clear maybe. If we now take A to be the free Kronecker, oops, and then we let B be the path algebra given by the 2 Kronecker given by alpha 1 and alpha 2. Then we have that the fundamental group is the free group from 2 generators given by the 2 poles that we have here. For example, the generator alpha 2 minus 1, alpha 1. But then when we take the contracted fundamental group and quotient, we kill the generator alpha 2, alpha 1. Since if you look earlier at the definition, in this case, to kill this generator, we can just note that we can pick V to be the trivial walk, and then U to be alpha 1, and then U prime to be alpha 2. And then this is precisely a generator of our normal subgroup, so this is killed when quoting, and then we just get Z. So it's kind of like we're contracting this hole, and this hole doesn't exist anymore in the B coin. Okay. So what is the connection then with relative Hochschild? So now we need to find a relative presentation. So we take B to be some subalgebra, such B is generated by substitute arrows before. And then a relative presentation would just mean a presentation of the respective algebras, but such that this square commutes. And now, lastly, we need to find what happens to the parade data in the relative setup. Okay, so this will be a definition by picture. So I will explain now what the picture says. So we assume throughout, of course, that A is connected as quiver. And then the thing is, though, now we pick the subset of arrows in B, generate B. This need not be connected B as a quiver. So then here, gamma 1 to gamma I, the big gamma, we denote the connecting components of our quiver that's given by B. And then what we do to pick a relative array data is then defined to be a parade data where in each connected component we fix a base point and we pick the parade data there as normally. We pick it locally in each connected component of B, and then globally to make this global from our global fixed base point, we then pick a walk from that base point star to every local base point. And in particular, we can note that relative parade data is just a kind of parade data. So it's just a specific kind of parade data, but it's parade data to patch locally. And then we've shown that we have an induced monomorphism then from the dual of the contract fundamental group into the first relative Hochschild cohomology, which is independent of the choice of relative parade data. And furthermore, we get that the following square that we had beforehand, where we can now put in something else instead of question mark, will also be a pullback square. It looks as follows. And then if one is interested in the non-vanishing of the Hochschild cohomology, then of course it suffices to find the non-vanishing of any of these things here appearing in the square. So particularly if the contract fundamental group is non-vanishing, then the Hochschild cohomology is non-vanishing. So as a last example, let's just look what the contracted fundamental group looks like in the group case. So if G is a finite group and L is a normal subgroup, and then again we take the presentation that we had before, we'll take the quiver with one vertex and one arrow for each element in the group. And then we have a relative presentation of the group algebras. And then one can note that, as we said before, pi 1 is just isomorphic to the group. So the dual of the fundamental group, since case trivial group module. It's just H1 of the group with coefficients k, so the group homology. And then similarly, one can show that the contracted fundamental group in this case will be isomorphic to the quotient of G times L. So in this case, the dual fundamental group will be the first group homology with trivial version of the quotient. So one way to think about this example is that it tells us that somehow relative Hochschild homology or relative behaves similarly to taking quotients. Okay, that was all I had to say. Thank you very, very much for listening.
Thank you, Jonathan. Wow, it's very interesting. Do we have questions for Jonathan?
I think I have one or two questions. When a long ago, I look a little bit at those H1, etc., and there was every time the first Hochschild cohomology group has a subgroup that is the subgroup generated by the derivations that are
Diagonal.
diagonalizable.
Yeah, the diagonal derivations.
Yes, and we did this kind of showed that does this. I think does this also, uh, for instance, when the all the algebras were when does the generate the whole H1. I think we showed. I'm not sure anymore. We showed that the algebra is solvable. I think when all I think we have to look. This is a paper that I did together with other people long ago. I really forgot. Other kind of derivations that we had, that in characteristic zero, all derivations have this property, is what we call integrable derivations. Even showed that when G is a group whose order is if KG is not semisimple, then there are always derivations that are not integral. And those derivations that are integral, they also for the inner derivations, they are integrable always, so they form a group. And so I think that perhaps would be a nice thing to look here to see if we can say what is, for instance, relatively diagonalizable now. I don't know.
Yeah, so the thing you get is that the image of this map will be diagonal derivations in general. The image will be a torus of HH1. And then Briggs and Rubio y Degrassi show that any maximal torus can be given by the image of some presentation of the fundamental group. So, but yeah, the integral ones I have not looked about. So this is very interesting. Thank you very much for the question. This I will definitely look into.
Great. Are there any other questions? I have one, like a curiosity. Is the pi one and this home dimensions easier to compute than the first Hochschild cohomology group?
I would say so. In general, pi one is easier to. I mean, depends on what. Okay,
Or maybe it depends on the algebra, I don't know.
depends on the algebra, I guess. Sometimes, but I would say it's at least quicker than.
Xavier, I didn't understood what was the question.
If the pi one and is easier to compute than the Hochschild cohomology than this first group and all these home spaces.
Yes, sometimes yes.
Yeah, I would sometimes it's definitely easier. I mean, even for monomial it can be quite hard to compute.
For a monomial is the fundamental group of the quiver.
Yeah, but even for monomial, the HH1 can be hard to compute. I mean,
Yes.
for example, for gentle algebras, there's a long computation to give precisely the generators of HH1 of A. But as you say, for the fundamental group, it's just you just take the quiver and you just look at because it's just as a graph. So there you have an example, for example, where maybe it's easier to compute the fundamental group than computing the actual HH1.
I see. Thank you. So any
Nice talk.
yes, very nice. If we don't have more questions or comments, thanks, Jonathan. Thanks again.
Bye-bye.
Really, really nice.